what I'm going to be talking about today is if we are to build models for learning under uncertainty, what should these models look like and what should they do? Before we do that, I just need to define what... That's not very big, is it? Did I? There we go, that's better. In order to do this, we need to first define what learning is. So for the purposes of this talk, I'm going to define learning as updating beliefs or inferences over time. And in order to deal with this type of question, we're going to need a model that can deal with probability. In a Bayesian sense, your belief is a probability, and we also need to be able to use time series data. In an ideal world, these models should be efficient. The brain can't really store everything, and ideally less computation would be better. And also this idea of inference, right? It's about taking what you've observed and working out some kind of abstract rule or some kind of structure. So ideally, we want our models to be able to kind of compensate for that as well. And I'm going to propose to you over the course of this talk that a coupled hidden Markov model is the way to go. So rather than dealing with lots of equations today, I'm going to switch to talking about graphical models. But first of all, I'm going to explain how this equation relates to a graphical model. And basically, this graphical model just specifies relationships between these variables. And as you can see here, for instance, on this blue link, you can see that there's an arrow from V1 to V2, and that means that V2 is conditionally dependent on V1. And anything in front of this line means it's conditioned on. So here, V2 is conditioned on V1. And we can write any probability distribution in this particular way. But now I'm going to show you what happens when you take away a link. So I've removed the green link here. So V3 is now independent of V1, as long as we know what V2 is. And I'll explain a little bit more about what that means in a second. But essentially, I've just removed the green link down here. We've still got the blue, we've still got the orange, but I've just taken away the green link, right? So what is independence? Why does it matter? Why have you taken away that link? I'll start with a kind of simple example of what independence is. And the simplest one I can think of is that rolls of a dice are independent, right? And that essentially means that knowing the outcome of the previous roll of the dice doesn't tell you anything about the next roll. So, for instance, if you were to calculate the probability that you roll an even number on the first roll and a multiple of 3 on the second roll, that just equates to to multiplying together the two separate probabilities, right? And we can express this a little bit more neatly mathematically down here. And the same thing holds for conditional independence, right? When we've got conditional dependencies between variables, we can define conditional independence as the probability of A and B given C is equal to the probability of A given C times B given C. So again, we're just separating out the two variables before they're kind of given or conditioned on line. Now, I've taken the graph on the right-hand side of a previous slide, and I've just stretched it out so that rather than it being in like a triangle shape, it's in a line or what you might call a chain. But the equation is the same. And through some simple probability theory that I won't bore you with, we can show that if we condition on, so if we think that we've observed the value of V2, then we do indeed get this formula for conditional independence. So given V2, V3, and V1 are conditionally independent. Now that I've talked through what a graphical model is and how we're going to use them, I'm going to define our kind of target model, which is a coupled hidden Markov model. And I'm going to start from the end, actually. So I'm going to define a Markov model, then I'm going to talk about what it is to be a hidden Markov model, and then coupled hidden Markov model. This is the same graph as I showed you just before. And we can now think of this as the building blocks for our Markov model. Those haven't animated very well. But essentially, this is the same equation as before, with the same links. And on this step, all I've done is I've transformed this product into this term here. So this kind of large N is just a posh way of saying product of these two. If you had lots and lots and lots of these, then it would make sense to use this notation rather than this notation because it wouldn't all fit on the slide. Doesn't seem to help much for 3, but if you had like hundreds, it would help. And we can think of this term here as a transition probability, and that's going to define how our variable changes with successive time steps. Just to reiterate again, we've got this conditional independence going on. So we know that given v2, v1 is independent of v3 and vice versa. Now I'm going to do something slightly cheeky, and I'm going to swap our numbers for words. So if we say that v1 is the past, v2 is the present, and v3 is the future, we can arrive at the Markov property, right? Which is that given the present, the future is independent of the past. And just to note here that this property is as much as it's an assumption as much as anything else, and it's basically just there to help us to simplify our calculations and to reduce the amount of computation that we have to do. Now moving on to what makes hidden Markov models hidden. So as I discussed, the transition probabilities characterize Markov models or Markov chains, and we can describe. In hidden Markov models, we can think about this hidden state, right? This thing that's governing the rules of our environment, and we can describe how it evolves through a Markov model. And then we can say that this hidden state gives rise to observations, which we can see and we do have access to through this emission probability. And crucially, we're going to assume that the observation at time t depends only on the hidden state at time t. So this gets us back to the idea that we want our model to do what we're able to do, in the sense of we want to be able to take things that we have access to and infer about things that we don't have access to. So to put this simply, initially we start off with this hidden variable here and this observed variable, v, or visible. And I'm going to introduce this kind of separation. So we've got things that are not observed, which is the hidden state, and things that are observed, which is the observation. And we can see that our initial emission probability comes in here, and I'm going to build this up piece by piece, right? But before we move forward in time, this is how the first observation is generated from the first hidden state. This we've already seen before. This is a Markov model or a Markov chain, and we saw this equation earlier, just in slightly different terms. And we've got our transition probabilities here again, but this is exactly the same as you saw a few slides ago. Now we can bring together the previous two slides and demonstrate a full hidden Markov model for the three states. And we've got our initial emission probability, the rest of our emission probabilities at various times, and our transition probabilities. So again, this might not seem particularly helpful for three variables, but I'm going to explain in a minute how it will be more useful if you have lots of time steps and lots of variables. And a common task that people do with hidden Markov models is to do this process called filtering. So you take all the observations that you've got up to a current time point, and then you work out the value of the hidden state at that time point as well. And so to kind of put it simply, you compute the current value of a hidden state given previous observations. And just to think about efficiency for a minute, even in this very simple three-state model, or kind of three-time step model, we can get rid of all these dependencies by assuming that we've got a hidden Markov model, and the amount of links that you can get rid of, the amount of arrows that you can get rid of, scales with the number of variables that you've got. So if you've got like 100 variables, you end up saving like, I think you get rid of 50 times more links than you actually save. So it's much more efficient if you assume that the data are generated by a hidden Markov model. So just to complete our discussion of what a coupled hidden Markov model is, I'll explain the coupling. And the coupling is essentially you just introduce a higher level variable, here I've called G, and you assume that both G and H evolve in a Markovian fashion. And what happens is that G will influence H in some way. So the higher level variables G will influence H in some way. So the higher level variables will influence the lower level variables. And for our purposes, they're going to control how quickly, or they are going to control the size of the changes of the lower variables. So you can put this in a posh way by thinking about it in terms of a Gaussian random walk with Markovian assumptions. But to actually make this more concrete, here we've got the range of values that hi can take, and the mean of this distribution, as it were, is the value of the hidden state at the previous time step. But with a low value of g, the kind of steps, like the vertical steps that the hidden state can take are quite small. Whereas if we have a higher value of g, the distribution is broader, and the hidden state can take much bigger steps, as it were. So this is how the kind of high-level variables control the low-level variables, or control the influence of the low-level variables. So that's all very well and good, but does it tell us anything about real life or behavior? I'm going to start off with something that's a little bit more real life. So in this slide here, I've got a sequence of heads or tails from the outcome of a particular coin. And we're going to work out what the probability of heads is, or we're going to think about how we would work out what the probability of heads is. And crucially, this is the exact process that I've been describing implicitly all the way along, which is just filtering a coupled hidden Markov model. So the first thing we're going to assume is that it's p heads, right? That's the hidden state. P heads is generating this sequence of heads or tails. So when p heads is high, there'll be lots of heads. When p heads is low, there'll be more tails than heads. You might also think that after about 8, you're getting more tails than heads, right? Which is unusual. So you might think that there's been a shift in p heads, right? So the hidden state itself has changed. So we're going to introduce some changeability. And finally, you might also infer that this switching between p heads being high to p heads being low seems to happen at different rates during the course of these trials, right? So the fact that the brackets are different color, so there's kind of this orange and blue, indicates that there's some changeability. And we can define this meta-changeability based on the arrow size, right? So how often do the brackets go from blue to orange? Now, to formalize this in a graphical model, which is a little bit of a wordy one at the minute, but bear with me, we can see that from what we observe a sequence of heads or tails. We've got our first hidden state, which is the probability of heads. And then governing the transition of this probability of heads is the changeability. And then we've also got this non-time varying meta-changeability at the top, which controls the arrow size, as it were. Now, to make this a little bit neater, to make this a little bit more formal, I'm going to borrow the notation from Tim Behrens and colleagues, but essentially we've got the same thing, just in different labels. So Y is now a head or a tail, R is the probability of heads, V is the changeability, and K is the meta-changeability. So we've kind of discussed how this is a little bit closer to real life, but we're not quite there yet. So in the task that Behrens and colleagues used, it was just a standard reinforcement learning task. So you learn by trial and error whether or not you should be picking blue or orange. But crucially, the probability that you will be rewarded if you pick blue changes over the course of the experiment. So in the first bit, it stays stable, and in the second bit, it changes a lot, right? So for this type of task, which is kind of common in neuroscience, in kind of cognitive neuroscience and psychology, I hope you'll agree that that slightly contrived coin flip example, the model that rests on is exactly the type of model that we should be using here, right? We've got periods where a hidden state, which we can see here, is changing, and it also changes at different rates. So we've got our changeability, we've got our meta-changeability, and we've got our hidden state. So just to complete this kind of metaphor, this is the same graph as before, but now the variables have got different meanings. And now Y is whether or not blue or orange wins. R is whether or not, R is the reward rate on blue, so probability that you win given blue. V is still the changeability, and K is still the meta-changeability. And just to reinforce the coupling between these levels, so the meta-changeability controls how the changeability changes. And then the changeability, in this case, controls the width of the beta distribution. So the probability is going to be between 0 and 1. So we know we need a beta distribution. And the variance of that beta distribution is controlled by the variable in the layer above. And then to go from this R into outcomes, we need to kind of do like a weighted coin flip. So that's how we end up going from the kind of lowest level hidden state until the outcomes. Now, I'm just going to briefly mention a kind of extension of this model. So this is the one from Tim Behrens, and this is from Chris Mathis and colleagues in 2011. This is the hierarchical Gaussian filter. And essentially, the models are the same, aside from the fact that this hidden state is a real number instead of a probability. And to get from the hidden state to the observation, there's a sigmoid transformation. But the important thing about this model is that it can be fit to individual participants. So Tim Behrens and colleagues, this model was just developed as a model. It wasn't actually fit to participants' behavior, whereas advances in approximate inference have allowed the same model to actually be fit to individual participants. So hopefully I've convinced you that for learning under uncertainty, in this case reinforcement learning under uncertainty, coupled hidden Markov models are the way to go. And the added bonus to using something like the hierarchical Gaussian filter is that we've got these different levels of uncertainty, and these uncertainties might map onto different pharmacological systems. Because we can fit the model to individual participants, we can understand individual differences in how people estimate and update their estimates of these uncertainty. And crucially for me, because I'm interested in psychopathology, we can understand how these individual differences might correspond to aberrant inferences or estimates of uncertainty, which may start to help us understand more about psychopathology in terms of stuff like anxiety. That's all from me. Thank you very much.